So there's a really useful skill called logarithmic differentiation, which is just another form of implicit differentiation. Is basically you take the natural log of both sides and then do implicit differentiation. There's two reasons you're going to do this. One is because it's impossible to take the derivative, because both the base and the exponent are functions of x. So that's one case in which you would do it. And the second case is it's just more convenient to use log rules to take the derivatives. And remember our log rules, like ln of ab is ln of a plus ln of b, and ln of a over b is ln of a minus ln of b, and then ln of a to the b is equal to b ln a. And by using the log rules, what it will allow you to do is it will just make it easier to compute the derivative. Like something like this, you could compute. It would require power rule, chain rule, quotient rule, like kind of a lot of mess in here. And we'll go through that example. So let's take a look at both cases. Now the process is pretty simple. You take the natural log of both sides and then do implicit differentiation. So let me just kind of show you how that works here. So you have x to the fifth root of x. We don't have that's not of our base definition. That's not something, and you can't think of it as like functions inside of function, like a chain rule kind of thing, because it's not like a constant, right? Like x to the x is not a base function that we can do. So you can't use like some tricky things, but you can do this. So y equals, x, and then instead of, we'll make this x to the 1/5, by the way, so we can do power rule because that's fifth root, and then you take the natural log of both sides, so you get ln of y is equal to ln of x to the 1/5. Now the advantage of the ln is the exponent gets to pop out in front here, x to the 1/5 ln of x, and now we can take the derivative of both sides, because this I can do as product rule because I've popped that exponent out in front. So this is derivative of natural log is 1 over y. Then by implicit differentiation or chain rule, I got to do times the dy dx. Here we're going to do product rule. So we're going to do derivative of that, which is 1/5 x to the negative 4/5 ln of x, plus this guy times the derivative of ln of x, which is 1 over x. Right? And if you do that one, this becomes 1/5 x to the negative 4/5, just to simplify a little bit. This is x to the 1. You subtract the exponent plus x to the negative 4/5. When you divide two fractions, same base, right? You subtract their exponents. And then you just multiply by y to then solve for dy dx. Is y times this. You could factor out the x to the negative 4/5 if you wanted to, but I'm not going to do that much work. And then last step is if you want it in terms of x, you know what x is because y is equal to this whole thing. So it's x to the 1/5 times this. You just replace the y value because we define this as y, right? Like that. Okay, so that's logarithmic differentiation. It's more of a process, not a formula or anything. Some books will treat it as a formula. Just think of it as a process. You're going to take the natural log of both sides, right? So let's make this y. We'll take the ln of both sides. And the whole purpose, like why do we do this, is because the exponent gets to pop out in front. That's the only reason. And then we'll just do implicit differentiation, right? So this becomes 1 over y times dy dx. And then here we'll just treat as product rule. So derivative of x squared is 2x. Leave the other side alone by product rule. And then plus x squared times the derivative ln. ln is 1 over whatever is on the inside, right? That's the outer function. And the inner function is this by chain rule. This also has an outer inner function. It's going to be negative e to the negative x because the derivative of negative x is negative 1. Plus derivative of sine x is cosine x, like that. And then you just move the y up, right? Multiply by y. Move this to, so make this y times all of this. And then the y is this whole thing. E to the negative x plus sine x, x squared times all of this stuff. Which is, this in case, very messy. But you at least get an answer. And sometimes in math, when you're solving things, at least having a possible answer. because there's lots of problems out there where we can't even get an answer. But you get an answer no matter how ugly it is, right? This is our answer right here. Okay, now let's talk about the second case when it's just sort of more convenient. Like you could do the derivative of this with enough patience. First, we're going to make this to the 1/2 power, okay? But let me show you the advantage of using logarithmic differentiation in a case like this is because if you take the ln of both sides, then you can do a lot of your more fancy. So first we can move the 1/2 in front, right? That's our exponent. Then we can split them apart from our log rules into, I'm adding these two, ln of x plus 2 plus ln of x minus 4. And then because sine x on the denominator, minus ln of sine x. Right? ln of y. And then we can take the derivative of both sides. So we're still doing logarithmic differentiation, but the derivative of this part is really easy. This is 1 over y dy dx. And this is 1/2. And then let's just take the derivative of each of these. This would be 1 over x plus 2. The inner function is not x, so multiply by the derivative of that, which is just 1. Plus 1 over x minus 4 times the derivative of the inner function x minus 4, which is 1. Minus 1 over sine x times the derivative of sine x, which is cosine x. And look at that. The dy dx is really easy to solve for. You just move the y up now to here. Right, so it's 1/2 times y, and y being this whole thing here, square root of x plus 2, x minus 4 over sine x, times 1 over x plus 2 plus 1 over x minus 4, minus cosine over sine x, like that. Or you could write that as cotangent x if you wanted to. Right, and so that would be our answer. Now, that is a lot simpler than if you attempted to do this directly. So let's say I wanted to do just without logarithmic differentiation, right? It would be x plus 2, x minus 4 over sine x to the 1/2, is you'd have to do power rule, 1/2, just to illustrate why this would be kind of annoying. I'm going to start it. And then, so that's power rule. Right, 1/2, subtract 1 on the exponent. Then the inner functions here, which I have to do quotient rule, so I got to do bottom, times the derivative of the top. Top derivative, I got to do product rule. So derivative of this guy is going to be derivative, that's 1. It's going to be x minus 4 plus this times the derivative of that, which would be x plus 2. Then minus top times the derivative of the bottom, right, divided by bottom squared. So it's very doable. This one's okay, but you can see, like, as I add complexity into here, some of the log rules just give you advantages to simplify out. So that's the that's the other second reason we might use logarithmic differentiation. And you might ask, like, Alan, are these the same? With enough algebraic manipulation, you can prove that these two are the same, but it would be tricky. But yeah, that's the idea of logarithmic differentiation. It's a process. So I don't think of it as a formula. Just think of it as we're going to take the natural log of both sides, do implicit differentiation, and then resubstitute the y back in when we're done. Thanks for checking out this video. I hope you found it really helpful. If you'd like more support, maybe you need more multiple choice practice, maybe you just need more guidance and things like that, I have plenty of information on my website. If you look in the description below and go to www.bothellstemcoach.com, I will explain all the ways I help students be successful in their AP classes.